Have you ever wondered why power companies talk about something called kVA, or kilovolt amperes, instead of just kilowatts when discussing system capacity? It might seem a bit confusing, especially when we are used to thinking about power simply as watts. Understanding this distinction is key to truly grasping how alternating current electrical systems operate efficiently and safely. Conceptually, apparent power represents the total power that appears to be flowing in an alternating current circuit. Think of it as the total capacity of an electrical system or component, measured in volt-amperes, or VA. It is the product of the total voltage and the total current, without accounting for any phase difference between them, giving us a complete picture of the electrical load on the source. The why behind apparent power becomes clear when we consider the three fundamental types of power in AC circuits: real power, reactive power, and apparent power. Real power, measured in watts, is the actual power consumed by a load to perform useful work, like lighting a bulb or spinning a motor. Reactive power, measured in volt-amperes reactive, or VAR, is the power that oscillates between the source and the reactive components, such as inductors and capacitors. It does not perform useful work but is necessary to establish magnetic and electric fields. The phase difference between voltage and current in AC circuits, caused by these reactive components, is what differentiates real from apparent power. To understand this practically, imagine pouring a glass of beer. The beer itself is the real power, doing the useful work of quenching your thirst. The foam on top is the reactive power. It takes up space in the glass, contributing to the overall volume, but does not quench your thirst. The apparent power is the total volume of the glass, including both the beer and the foam. Engineers calculate apparent power by taking the vector sum of real and reactive power, often visualized through the power triangle. This calculation allows them to properly size components like transformers and generators, ensuring they can handle the total electrical demand, including the power that does not perform direct work. This holistic view of power introduces us to the power factor, which is the ratio of real power to apparent power. A power factor close to 1 indicates that most of the apparent power is being used for real work, signifying an efficient system. Conversely, a low power factor means a larger portion of the apparent power is reactive power, leading to inefficiencies and requiring larger, more costly equipment to deliver the same amount of real power. This distinction between real and apparent power is why electrical equipment is often rated in volt-amperes, ensuring systems are designed to handle both the working power and the power needed to establish necessary fields. Ultimately, understanding apparent power is essential for designing and operating robust electrical systems. By recognizing that apparent power accounts for the total electrical capacity, including both the power that does work and the power that supports the magnetic and electric fields, engineers can ensure that components are correctly specified. This prevents overloading and guarantees efficient energy delivery, leading to more reliable and cost-effective electrical infrastructure.